Hello everybody, thank you for joining me for another recording for Edexcel's Year 13 Pure Maths course. This time it's Chapter 1, the first bit of the course, Proof, which, as I mentioned in the previous video, I've split into two parts because proof by contradiction is rather large, has lots of different examples and slight twists and variations on the theme, and tends to be a topic which students tend to not like. So I thought it was worth doing this across two videos rather than just for one. And we're going to focus this time on the classic proofs, the irrationality of root 2 and some variations on that, and of course maybe the most famous one of all, the infinity of the prime numbers. The warm-up focuses on understanding more deeply why the primes are infinite. So the warm-up sort of goes on a bit and almost repeats itself, but I'm very keen on giving you a deeper understanding, I should say, of why the primes are infinite, rather than just regurgitating the proof because you get the marks that way. Understanding is always better. Anyway, enough of me. I'll show you the warm-up questions now that I want you to attempt, or I'd suggest you attempt. So here they are. Try them now on your own, press pause now, and then press play when you're ready to see the solutions, and hopefully yours will match to mine more or less. Okay, so assuming you've done that, let's have a look together at the solution to warm-up question 1. So, the fundamental theorem of arithmetic is that any number can be written as a product of primes. Going back to GCSE, like the prime factorization of any number. So Marcion thinks he's discovered another mini-theorem, and this is true, that if a number is prime and greater than 2, then it can be expressed as one more than a product of primes. So we're going to show this is true with a few examples. So by considering prime factorizations, let's show this is true for primes 3 to 13 inclusive. So quite obviously 3, that's just going to be 2 plus 1. So 2, product of primes, so you can think of it as 2 times 1 plus 1. So 3, that obviously works. The next prime is 5, so I can think of 5 as being 2 times 2. That's a product of primes plus 1. Sometimes there's more than one way of doing this. The next prime after 5 is 7. I can think of 7 as 2 times 3 plus 1. 9 isn't prime, 11 is, and 11 I can think of as being 2 times 5 plus 1. And finally 13, I'm going to write this as 12 plus 1, and 12, of course, I can do as 2 times 2 times 3 plus 1. So essentially, hopefully this does give you some sort of idea and convinces you more than me just saying it, that actually any prime number can be written as a product of primes plus one more on top. That is true of any prime number. But the converse isn't true. Just because a number can be written like this doesn't mean that it must be prime. So the converse of this statement is that if a number can be expressed as one more than a product of primes, it's got to be a prime number greater than 2. So we're going to disprove that now by use of a counterexample. So there's infinitely many examples you could have picked to disprove this. I'm just going to go for this one, 10 for example. So 10 I could write as a product of primes because 10 is 3 times 3 plus 1 extra. But of course 10 is obviously 2 times 5. We know that 10 isn't prime. So therefore, a number one more than a product of primes is not necessarily prime itself. It might be, but not necessarily. But going the other way, if we are told that a number is prime and greater than 2, then this way round, it can always be written as a product of primes. But the other way, the converse, not necessarily. Let's now have a look at warm-up question 2. So now what Marcion's going to do is to consider all the individual primes, and he's going to label them as such. So P subscript 1 is the first prime number 2, P subscript 2 is the second prime number 3, P subscript 3 is 5, and so on. So he's listing all the primes consecutively. He's now going to consider the divisibility properties of numbers that are one more than a product of all these consecutive primes starting from P subscript 1. So in general, N subscript N is all the primes up to the nth prime number plus 1 extra added on top. So for example, N subscript 5 is the first 5 prime numbers consecutively all multiplied together, the product of those plus 1 added on top. So first of all, for part A, by considering divisibility, explain why n subscript n is not going to be divisible by any of P1, P2, all the way up to Pn. Well, it's not going to be divisible by any of the previous P1, P2 up to Pn, because that would always leave a remainder of 1, because of its plus 1 contained in the construction of n subscript n. So to just illustrate this with an example, let's go for n subscript 5. If I did n subscript 5 and, for example, tried to divide it by one of the primes up to Pn inclusive, for example, dividing it by P1, this is what it would look like in terms of fraction. Now, any fraction like this can be split into two separate fractions. So if I partition it like so, then this here, you can see that's the remainder. So this is the quotient, remainder is 1. P1 on top, P1 below, so you can see that would cancel. So we're just going to have P2, P3, P4, P5, then the remainder of 1. So filling in, if you want to, what P2, P3, P4 and P5 actually are in terms of numbers, we've got that it's 3 times 5 times 7 times 11 with remainder 1, and that gives us 1,155 remainder 1. And it'd be a similar idea if we divided n5 by P2. Same idea, but now the P2s would cancel, leaving remainder 1. Divided by P3, the P3s would cancel, but again, you'd always have this remainder of 1. So keeping it short and simple, it can't be divisible by any of the Pn because you'd always have a remainder of 1. However, part B, if nn is prime, why will it be a larger prime than any of the individual primes P1, P2, all the way up to Pn? This is actually quite obvious if you think about it. I'll just section this off here so it doesn't get confused with part B. But essentially part B, nn is a product of all these primes. So the largest prime is the last on the list, Pn, but n subscript n is a product of all the primes, plus an extra 1 added on top. So I'm taking Pn, and it's going to be multiplied by P1, which is 2, P2, which is 3. So because I'm multiplying Pn by other natural numbers that exceed 1, this product of all these, which includes Pn, will have to be bigger than Pn itself. So how to word this in a simplistic way? I'd say putting something like this for part B. If nn were prime, it mustn't be any of the P1, P2, all the way up to Pn, as we've shown in part A. So therefore, the only other solution must be that if Pn, this list, represents all consecutive primes up to Pn inclusive, then nn must be a bigger prime that is beyond Pn somewhere. It's got to be Pn plus 1 or Pn plus 2 at the very least, because this product is going to be huge, much bigger than just the individual P subscript n. Question 3, same theme. Marcian's going to decide to list all the n subscript n's for n being from 1 to 7 inclusive in this table here, so you can analyse some properties of a number and its construction. So we're going to complete the table. The first 2 rows have been done. So when n is 1, n subscript n is just going to be the first prime, add 1, which is 3. N subscript 2 is the first 2 primes plus 1 added, which is 7, which is prime. So let's carry this on. N subscript 3. Whoops, that was a mistake. So this is going to be the first 3 primes plus 1. Multiplied together, sorry. So that means 2 times 3 times 5 plus 1. And so using the calculator, we can actually work out what this is. So 2 times 3 times 5 plus 1, that gives 31. Now you could check on the calculator if it's prime or not using the fact function, but I can tell you that actually 31 is actually a prime number. If you want to check it, I'll show you how to. So we get 31, press equals, then press shift fact, and the number doesn't change. So 31 is prime, so big tick. Therefore, prime divisors, don't need to worry, because 31 is prime. So, n subscript 4, the first 4 primes multiplied together, then 1 added on. So that's going to be 2, 3, 5, 7 plus 1. Let's see what this gives us. So now just altering this, going to times by 7 as well. That gives 211. Is this prime? Well, let's check. Press equals, then shift, fact. Yeah, it doesn't change. So that again is prime, so no new prime divisors for that number. N subscript 5. This time it's getting a bit too much to write on. So it's the first 5 primes multiplied, then plus 1. So if I just adapt what I have here, first, second, third, fourth prime. The fifth prime isn't 9, of course. The fifth prime is going to be 11. That gives 2,311. Is this prime? So press equals, shift, fact, answer, shift, fact. It doesn't change. So again, 2,311 is prime as well. But keep going. N subscript 6. The first 6 prime numbers, then plus 1 on top. So if I just toggle back here, the 6th prime is going to be 13. 1, 2, 3, 4, 5, N subscript 6, then add 1 on top. We get 30,031. Is this prime? It's pretty big. Shift, fact. Oh, it's not. It's got 59 and 509, so it's not prime. New prime divisors are 59 and 509. One more, final one, N subscript 7. So same idea, but this time we're going to go up to the 7th prime. The 7th prime is going to be 17. And of course that plus 1 added on top. Pretty huge number, 510,511. So to check if this is prime or not, we do shift, fact. No, look, we've got 19, 97, and 207. 277 rather. So no, we've got 19, what are the other two, sorry, my bad. 97 and 277. Now before we move on to the next warm-up question 4, just have a look here. For the cases from where n is prime, let's just have a look. When n is prime, what's happened here? Well, there's no new prime divisors, but look at what nn is itself. So when n is 1, the first prime number is 2, 3 is bigger than 2. When n is 2, the second prime number is 3, 7 is bigger than 3. 31 is bigger than 5, 211 is bigger than 7, and 2,311, of course, would be bigger than the 5th prime, which is 11. So when nn is prime, it would seem to be that nn is always greater than the last prime used in its construction, which is Pn. And down here, we can see that when nn is not prime, we have these prime divisors which exceed the current last prime used in the construction of n subscript n. 59 is much bigger than the 6th prime number, as is 509. And the 7th prime number, which I think we said was 17, we generate bigger primes beyond nn. It always has, so therefore when it's not prime, it always has some prime divisors greater than the Pn up to that point. So just to crystallize this with warm-up question 4. So essentially saying what we said using the table. So going back to the table, obviously we see that n subscript n plus 1, it's not always prime. For the last 2 rows it wasn't. So when it was prime, the magnitude of the new prime number it was compared to the last prime on the list, we just saw that when nn is prime, n subscript n is bigger than the last prime used in the construction of n subscript n. And for part B, again, like we've seen using the table, if I could speak properly, for the cases where n subscript n is not prime, make a comment on its prime divisors compared to the individual p1, p2, all up to p subscript n. And like we've just seen before, the new divisors, prime divisors I mean to say, are going to be new ones that aren't in the list up to pn. So when nn isn't prime, it has at least one new prime divisor not yet listed up to the list p subscript n. And so the warm-up questions will tie into, hopefully, an understanding of the last worked example of the infinitude of primes. But before that, let's get started now by having a look at some more examples on proof by contradiction. So some further examples using proof by contradiction. We've seen how fairly simple results can be proven indirectly using the method of proof by contradiction in the last subchapter. The method of proof by contradiction is readily adaptable for a wide variety of problems for A-level. The examiners will not only expect you to be familiar with a general setup for a proof by contradiction problem, but to also be able to adapt standard proofs and results. For example, the classic proof of the irrationality of root 2, which we'll see later, should not only be known but also understood, lest, in other words, so that you don't become panicked when you are asked in an exam to prove the irrationality of root 5, say, because we can adapt this irrationality of root 5 because it will closely follow the setup and structure for the proof of the irrationality of root 2. As ever, the best course of action is plenty of mindful practice, not just practicing any random questions, but in particular focus on the questions which you need more help with and the ones which are more likely to come up in an exam or of a similar style to that. In terms of preparation for these adaptations, we'll have a look at some adaptations together before commencing the suggested exercises, which essentially is exercise 1A from the textbook. So let's begin. Worked example 1. Let's prove by contradiction for all n being natural numbers that if n squared is even, n itself must be even. This, I believe, in my opinion, confuses students because it seems back to front. You take n and then you'd square it. That's what we've done from GCSE, whereas here it's almost in reverse. We're starting with a premise about n squared, then considering n itself. So because there's no direct root, because you'd be getting into square roots with algebraic representatives, it'd be awkward. We need to use proof by contradiction. As ever, we start with a negation. So first step, we negate this. The negation is to assume there exists an n such that n squared is even, like it says, but n itself is odd. If such an n exists, that disproves this statement here, which would show that actually this statement is not true. So what we need to do now is to prove that this assumption is a load of nonsense. If this assumption is nonsense, then the conclusion must be this original statement is true. So, right, we've got that n squared is even, but n itself is odd. So if n is odd, let's define this algebraically. If n is odd, let n be 2k plus 1, where k is a natural number. So 2k is even, add 1 to an even number. This is a robust algebraic representative for any odd number. So we've got a representative for n. Let's now square it. So if that were the case, n squared would be 2k plus 1 all squared, which of course is 4k squared plus 4k plus 1. Our objective here is to show that this here must be odd. So what we're going to do here is we're going to factorize out the 2 to emphasize that this is going to be one more than a multiple of 2. So we've got two lots of 2k squared plus 2 plus 1. This, of course, is even, clearly. It's some multiple of 2 plus 1. So this value here has to be odd. However, we've just said that n squared is even. But we followed this assumption through logically and ended up with a complete and utter contradiction. So it contradicts our assumption that n squared is even. But apart from this assumption, all our steps were logical and completely and utterly fair enough, and it's come out with some absolute nonsense. If all the steps have been logical, but we've ended up with a nonsense, the only conclusion must have been that the original assumption itself was built on a house of cards and was not true. So because of this contradiction, we can therefore conclude that the original statement, this, must be true. So therefore, if n squared is even, it's got to be that n itself must have been even too. And this little square is just a fairly old-fashioned formal way of writing down that the proof has been finished. That's like almost a mathematical full stop you can use if you like, but normally is used for proofs or after proving a theorem. If you study maths at university, you might see this more. Let's try another one. Worked example 2. Prove by contradiction that there exists no integers n and m such that 3n plus 21m could ever equal 137. Again, we start with the negation. What would be the bare minimum to disprove this? We could say something like this, that there actually do exist integers n and m such that 3n plus 21m is 137. This is a very simple negation. This statement is just saying there are integers n and m such that blah blah blah. We just now say there are integers n and m such that. Whereas the saying there's not integers, we're now saying there are integers that could exist. So then we're just going to take this and just work on it algebraically. The first thing to notice is these are both multiples of 3, so we can factorize. So 3 lots of n plus 7m must be 137. We can now divide both sides by 3, so n plus 7m must be 137 over 3, and if you want to try that on a calculator, you don't need to. I'm hoping that's fairly obvious to you. That's not a whole number, and that's all that really matters. This is not a whole number, this is not an integer. However, n plus 7m has to be an element of the integers, because both n is an integer and 7m is an integer. M is an integer, so an integer multiplied by another integer gives an integer. Just going back to the previous video, we talked about that using the idea of closure. The integers are closed under the operation of multiplication. In other words, integer multiplied by integer gives another integer. So n plus 7m, the left-hand side of this, is an integer. However, the right-hand side is not. So what this is saying is integer equals non-integer, which is a nonsense. So what you need to do now is just to word it carefully to make sure you don't slip up and lose any marks. So the first bit we've got here, we've shown that n plus 7m has to be an integer. We now need to say that therefore n plus 7m therefore could never equal 137 over 3, because this is not an integer. In other words, we have a contradiction. We're saying here an integer can equal a non-integer, which is a contradiction and a nonsense. So now we say this contradicts the assumption that 3n plus 21m could ever be solved to equal 137, where n and m are integers. It just can't be the case, because we've assumed it to be the case and got an absolute nonsense. Therefore, the only conclusion must be that there are no integers n and m such that 3n plus 21m would give you 137. We're not saying it can't be solved. All we're saying is it can't be solved using the integers only. Let's move on and have a look at a third worked example. Worked example 3. We're going to prove by contradiction that if a is a rational number and b an irrational one, then a minus b, the difference between them, has to be irrational. First of all, the negation. So we're going to assume there exists a rational number, call it a, and an irrational number called b, such that the difference, a minus b, is rational. So if a is rational, let's define it as a rational number. Call a some letter over another letter. We've used a and b, so I'm just doing c over d. Remember, the definition of a rational number is it can be expressed as a fraction in its simplest form. So to be clear and accurate of the examiner, I've termed what c is. So c is an integer, and also I've put here d is an integer, not including the element 0, because obviously we can't divide by 0. So it's important and good practice to add in this condition as well. Next, because a minus b we're assuming to be rational, let's also call this itself a fraction. So we'll let a minus b equal e over f. In the same way as before, state clearly that e is an integer and f is a non-zero integer. Now we can do some manipulation and end up with our contradiction which we need. So next step, let's imagine now a minus b. So of course we said a is c over d. So a minus b is just c over d minus b. So a minus b we've got as e over f. And we want to show that this is going to be rational. I can rearrange this now. We've said that b is, of course, irrational. So if I just add b to both sides, then take away the e and f, I can see that b has to be cd minus e over f. We can put this into a single fraction by getting a common denominator. Try this yourself, but hopefully you agree with me that as a single fraction, b is cf minus ed all over df. And because of the setup of this question, b is irrational. This looks like a fraction to me though, so let's just do some careful worded analysis on it. So cf minus ed. Well, cf minus ed is an integer. Upside down triangle here means because. This is because c and f is an integer and e and d are integers. If c and f are integers, the product will be an integer. E and d are integers, therefore the product ed will be an integer, going back to the closure idea under the operation of multiplication for the integers. And finally, integer minus integer will give you another integer. It's not necessary to explain to the examiner the concept of closure, but it is necessary to just give some brief explanation as to why you know, using the properties of number, that cf minus ed, this numerator, is certainly an integer. So do make that clear. It's important for the proof and to pick up the marks. We now need to mention similar for df ideally as well. So next, by the way, just a little thing here in green. This is optional, so I was put it in green. You could say, if you wanted to examiner, the integers are closed under the operations of subtraction and multiplication. This is why this thing in blue holds. Again, like I've said, mentioned about df, say that df is also going to be an integer because d and f are integers too. And going back to this idea, integers are closed under multiplication. So if b is a fraction, and we've shown that the numerator is an integer, and the denominator is an integer, then by definition, we've shown that b must be a rational number. So therefore, cf minus ed over df, that's got to be rational. However, hold on, it says b is irrational. So we've just contradicted ourselves. Bingo, this is what we want to happen. So this contradicts the assumption that b is irrational. Once you've got your contradiction, go for the kill. The end game now is to conclude that the original statement must have been true. Our assumption must be wrong because we have a contradiction. Therefore, it has to be the case that if a is a rational number and b is irrational, a minus b will also be irrational every single time. Worked example 4. We're going to prove by contradiction to show that there are no positive integer solutions to this equation here, 4a squared minus b squared equals 5. So what could we really do with this? 4a squared minus b squared. I'm hoping you'd consider using the difference of two squares. First of all, though, we need the negation. So we are going to assume that there do exist positive integers a and b that satisfy this equation. We can take this and factorize using difference of two squares. So 2a plus b, 2a minus b equals 5. Well, how can this be the case? We're assuming that a and b are integers. So in this bracket will live an integer. The second bracket must be an integer. So integer multiplied by integer gives us 5. How can that happen? Well, there's only two possibilities. Either 2a plus b is 1, and this is 5, or 2a plus b is 5, and this is 1. So just considering the two cases, it has to be the case that either 2a plus b is 5, 2a minus b is 1, or the first bracket is 1 and the second bracket is 5. However, using these two simultaneous equations, if we add both together, both this option and that option, we're going to get over here, the b's will cancel, we get that 4a equals 6, but over here too, using the second scenario, the only second scenario it could possibly be, we also get exactly the same, that 4a would have to be 6. Dividing by 4, that can only work if a is 1.5, but 1.5 is not an element of the positive integers, also called the natural numbers. So again, this is our contradiction. We've followed it through logically. This is the only way it could work, and the only way it could work is if we break our assumption itself. So it's a nonsense. So to conclude carefully, we have to say this contradicts our assumption that a and b are positive integers, because a can't be. And therefore, it can only be the case that the original statement was true. That's our concluding final step. So therefore, there are no positive integer solutions to the equation 4a squared minus b squared equals 5. Word example 5 now is a classic proof. We're going to now have a look at the irrationality of root 2. We can assume here, without proof, that if a squared is even, then a is also even for any natural number. This is essentially an identical proof to what we've seen before. If a squared is odd, then a has to be odd too. But we don't need to go in and prove that. And if this were to come up in an exam, and it just said proved by contradiction root 2 is irrational, then we could normally assume without proof this line here. What would usually happen is it would be a part B of the question. Part A might be to prove this second line here, and part B would then be, hence prove root 2 is irrational. So we can assume the second line. So again, we start with a negation. We're going to assume that root 2 is rational. And if it is rational, it can be written as a fraction. So let's write this out as our next step formally. So let root 2 equal a over b, where a is an integer, b is a non-zero integer, and this is absolutely crucial. It's a subtle point, but hugely important. We also need to assume that a and b share no common factors. Equivalently, we can say that a over b is a fraction in its simplest form. This is absolutely key. If you think about it, it's absolutely fair enough. Any fraction can be fully simplified. There doesn't exist a fraction that you can't fully simplify down to its simplest form. Any fraction has a simplest form. So it would be a nonsense to say there exists a fraction that can't be simplified. So just bear that in mind, because this will come back at the very last step. So we have this here. What could we do? Well, we could maybe square both sides. So if this is the case, 2 is a squared over b squared. Multiply both sides by b squared, we get that 2 lots of b squared is a squared. In other words, a squared is even, because it's 2 multiplied by an integer. So therefore, a squared is even, but using this here, if a squared is even, we can then deduce that a itself has to be even too. So we write that down. So from this, we can say, because a squared is even, a itself is even. Let us now represent a with a suitable algebraic representative. If a is even, we need to write it down as some multiple of a natural number. So let's introduce a as being 2 multiplied by k, where k is some other natural number. We can then substitute a being 2k into this expression here. So this line will become 2b squared equals 2k all squared. If we expand this out, 2b squared equals 4k squared, and now what we can do is isolate b squared by dividing by 2. So therefore b squared must be 2 lots of k squared. So we've just shown now that b squared is also a multiple of 2. So because b squared is a multiple of 2, it's even, and so b itself is even. So we've got this fraction a over b, but a is even and b is even. But if a and b were both even, they'd have a common factor of 2, and so wouldn't be in their simplest form, which is what we've assumed. So our assumption is wrong, therefore this is where we have our contradiction. So this contradicts the assumption that root 2 equals a over b in its simplest form. What we've shown here is root 2 cannot be written as a fraction in its simplest form, which is the same as saying it can't be written as a fraction at all, because any fraction has a simplest form. Now we can conclude, get the marks in the bag, and we're done. So therefore, root 2 must be irrational. It's now very important that we understand this proof in a bit more depth, because there's lots of different types of irrationality proofs which you might encounter in the exam. Of course you might not, but you're very likely to, so it's important to know how to adapt this idea. On that note, let's have a look at some adaptations together for you folks. So this is over to you now. So like I've just touched upon really, as with almost all of maths, questions become easier when you can begin to see the general patterns and themes running through similar problems. It's then much easier to adapt standard results rather than treating each question as a totally new mystery. So in small groups now, consider how worked example 5, the irrationality of root 2, can help with these 3 irrationality proofs below, and for each one, it should really go without saying, but I'm saying it explicitly here, you need to use proof by contradiction for each. And here are the 3 examples of colour-coded in red, green, and blue. So if you're watching from home, pause the video now and try these on your own, and press play to see my handwritten solutions. And as long as the theme follows through, it doesn't need to be exactly my same wording, you should hopefully see the structure of how worked example 5 can help us. Okay, so assuming you're in the class or at home and you've had a go at these, let's have a look now at the structures of these proofs. So proving root 5 is irrational, here's how I'd set this one out. Again, apologise for my handwriting, I'll give you a very brief talk through. So we're going to assume root 5 is rational, so let it equal a over b, same setup as before, look. 5 is a squared over b squared. In fact, I'll just let you digest this. There's no point me talking over as you're reading. So something like this for the first one. Moving on. Proving log base 3 of 8 is irrational. I'd suggest something like this. Negation, write it as a fraction, and then use laws of logs like this. Put them both to the power 3. 3 and log 3 will cancel, so you've got 8 equals 3 to the power a over b. If you take both of these sides and raise them both to the power b, 8 to the power b just becomes this, and 3 to the power a over b to the power b, the b's cancel as it were, we get this. 8 to any integer power will be even, and 3 to any whole number power will always be odd. So when we conclude like this, so 3 to the power a is always odd, 8 to the power b is always even. We've got an equation which says even equals odd. That's a nonsense contradiction. So log base 3 of 8 is irrational. Finally, the blue, proving that the cube root of 7 is irrational. Might look something like this. This time I'm just going to not speak and let you just have a peruse of that so you can digest it. Let me know in lesson or the comments if it doesn't make sense. Okay, let's now have a look at the final main course, one of the most famous proofs in maths of all time, the infinitude of prime numbers. So this goes full circle back to the warm-up now. So the infinitude of the primes. If 1 is added to the product of consecutive primes, beginning with the first prime, creating this number here, like we saw in the warm-up, then this resulting number is either prime or it's not. Obviously, it's got to be one or the other. There can only ever be these two cases. Go back to the warm-up questions if you need a refresher on this idea we're talking about. So case A. So if this number, add 1, is prime, then it has to be a much larger prime than any of the individual P1, P2, P1 used in its construction. Because this is a massive, huge product of lots of primes, and each one of these is going to be 2 or bigger. So obviously this is a huge product, much bigger than any individual prime. Thus all the primes from P1 through to Pn could not have been all the prime numbers, since this number plus 1 is prime and obviously much larger. So that's case A, if this number is prime. Case B, what if it's not prime? If it's not prime, then like we saw in the warm-up questions, it has to have some prime divisors other than any of the P1, P2 up to P subscript n, because if we did try to divide the number by any of these P1, P2 up to Pn's, it would have left a remainder of this pesky 1 here. Thus again, same conclusion, different case, all the primes from P1 through to Pn could not have been prime numbers, could not have all been the prime numbers. So either way you slice it, we're going to find the same conclusion, that the list of all the primes just was never complete. So either way, like I've said, you can demonstrate that any list of consecutive primes can never be finished. And this argument forms a basis of a proof, which I'm going to present now in what I think is a slightly simpler manner. Although I don't want you to think it's simpler than you see the proof and it's quite long-winded. It is quite long-winded. The proof I'm going to present to you is, in my opinion, a good mix of being fairly concise, but making good logical sense in a nicely worded manner. But this is slightly subjective. This version here, ask a different teacher, they might give you a slightly altered version, which I'm sure will be just as robust and just as valid, of course. So don't get too caught up in the subtle differences of the wording, the logic will hold. So here's my version of how I suggest we prove this. So let's go. Prove that there are infinitely many prime numbers. Start with the negation as ever, but this one has a twist. So what I'm going to suggest we do is not to simply assume that there are finitely many primes, but to have like a little embedded, subtle extra assumption here. So not only are we assuming there's a finite number of primes, but let's assume it in a slightly different way. Let's say there's a finite list of all the primes. So it's an embedded assumption. We're assuming there's a finite list of primes, which we can therefore, from that assumption, assume that we can have a list of them all. P1, P2, all the way up to Pn. This is all the primes listed, and Pn is the last biggest prime. Now imagine a big number, capital P, be the product of all of those primes through to the last prime. So capital P is every single prime consecutively multiplied together up to the last prime. Now we enter the masterstroke. Now let's imagine a new number, capital N, which is the list of all the primes plus an extra one added on top. Then either n is prime or it is not. If n is prime, it has to be a prime larger than Pn, the last prime. Because if n is prime, it has to be a bigger prime than the last one on the list, that list of all the primes could not have been complete. The list of all primes is incomplete. If, however, n is not prime, it must have, at the very least, one prime divisor not contained in any of the P1 through to Pn, as division by these would always leave a remainder of 1. So because if n isn't prime, it needs to have another prime divisor not contained up to Pn, that list of all primes must be complete. It must have missed some prime divisors. So same conclusion, the list of all primes must have been incomplete. So if n is prime, we conclude the list of all the primes didn't exist. If n isn't prime, we have the same conclusion. So either way round, we've shown that the list of primes can never, ever be complete. And that's our concluding statement. Therefore, there are infinitely many primes. I do appreciate it's quite a lot of writing, and you might feel that maths should be about just writing down the numbers and the quick calculations. So it's not a particularly popular topic, a proof by contradiction, but it is crucial that you understand how to do them and get to grips with the mechanics of what's going on behind the scenes. Anyway, that's enough from me now. That's all there is from the warm-ups and the worked examples. So now it's over to you. So the curtains come down, and now if you turn to page 4 and 5, exercise 1A in the Year 13 Pure Book. Try question 3 to question 10. Do all the questions, check them all, and please, please, please do let me know if you are not sure how to do any of the questions. Not knowing and then pretending it's fine is a recipe for dropping marks in the exam. So please do try and find it in you to have the courage and determination to try and work out the questions you're not sure of. Thank you very much for listening. I know it's been quite a stretch, probably quite hard to get through, but we've made it. So thank you very much for tuning in. Please do ask for help if ever you're stuck or unsure, and take care of yourselves. I'll see you all soon next time.